All right. Good. Yeah, thank you so much for inviting me to this and giving me the opportunity to present this paper here. This is joint work with a student from Max Planck Institute Informatics in Saarbrücken, Nick Fischer. It's about the computational complexity of Plethysm coefficients, and I want to try to define Plethysm coefficients. It's not so easy if you are not used to representation theory. So therefore, I'll go very slowly to walk you through the definition until we reach the Plethysm coefficient. And then I will talk about a combinatorial interpretation for Plethysm coefficients in some special cases. In some special cases, we have actually objects that count the Plethysm coefficient. We know it's like this special type of a number of some special objects. But this is only true for some special cases. But this is enough, actually, in the end, in the last chapter here, to prove that even deciding if a Plethysm coefficient is positive will be actually NP hard. Okay, that's the point. I mean, the whole point is now a hardness proof. The computation of the coefficient is hard, and even deciding its positivity is also NP hard. All right, I'll try to walk slowly through this. I mean, if you know representation theory, this will be really, really, really easy. Right? So a representation is a group of a group G is a finite dimensional complex vector space together with a group homomorphism from G to GLV. Okay, so let's just do some simple example. This is like the general linear group, right? Invertible linear maps on V. So say we take as a group now our toy example is a group with two elements. S2 has the identity and the transposition. Group with two elements, symmetric group on two symbols. Then if you say take the two-dimensional vector space, with this specific group homomorphism, this will be a S2 representation. So the identity element of the group will be mapped to just the identity matrix, and the transposition element, so this order 2 element in the group, will be mapped to the transposition matrix. Okay, this will be this is a representation, and there's a nice short notation that everybody uses, which is you can multiply a group element with a vector, and that's just well, it's just defined as mapping the group element using rho and then applying that to V. So this is amazingly intuitive, right? So the identity applied to a vector xy is just xy, and the transposition applied to a vector xy is just yx, right? So amazingly intuitive, nice notation for these things. And having a representation, making this vector space C2 a representation gives it additional structure. So C2 now decomposes actually into a interesting subspace here. Say, taking the vector 1, 1, we see that if we apply tau, it's fixed under this, under applying tau, right? It does not change. And actually the whole line, the whole linear subspace that is spanned by 1, 1 is fixed under applying tau. And here is another one that has a similar property, but slightly different. So if you take the vector 1, minus 1, and you apply tau, it actually switches sign. But the whole linear subspace is fixed under the operation. It's just the points are moved, right? They're permuted. But other than that, this one is also closed under the application of tau. Well, so this means, and this is a direct sum, right? So C2 decomposes in this nice fashion. And these are the invariants, and these are called skew invariants. And this is always the case. So whenever you have S2, any S2 representation W, you always decompose into some subset, some subspace, which are the invariants, and some subspace, which are the skew invariants. And you already see a representation theoretic coefficient now, which is, you say somebody gives you some representation W, then you want to know what's the dimension of the invariant space, right? So which is this one here, the multiplicity where the action is trivial. This is the dimension of the invariant space, and the multiplicity of where the action is x with a sign. This is the skew invariant space. Okay, I mean just the definition here, and these numbers are always non-negative numbers. They are dimensions, right? But already here is not so clear what they count, right? So the corresponding counting problem is not obvious because those are dimensions of vector spaces. Okay, and we will study a very specific type of representation, which is we want to study polynomials, homogeneous polynomials of degree, of some fixed degree, say in this case degree 2, in 2 variables. Okay, and that space has a basis, and the basis is just given by x squared, xy, and y squared. Right, so the W is a 3-dimensional vector space now, and you can define in a natural way. You can define an action of your group on this space, on your group with 2 elements. Okay, so you just want to define, if somebody gives you a polynomial p, what is tau p, right? So because identity should not change p, of course, but what does tau p do? And yeah, you define tau p by its evaluation on any vector x. So tau p of x should just be p evaluated at tau x. Notice we already know how tau x is defined. So you already have some definition, and you can lift it to the 2 polynomials now. So, but in this case, this is really, really simple. If you just see tau switches x and y, right? So tau of x squared is just y squared, tau of y squared is x squared, and tau of xy is just xy. Tau is literally just changing x and y here. And we already get some more interesting things now happening. So this is a 3-dimensional vector space, and it has a 2-dimensional invariant space and a 1-dimensional skew invariant space. There's already some interesting multiplicities happening here. And we go one step further, even one step further. We want to say, okay, and this is now going to be a Plethysm. We say, okay, we have our vector space W here with this basis x squared, xy, y squared. Let's now, and we know actually how tau acts on these on that vector space. So we rename the basis vectors and say, let's say x squared is now called A, and xy is called B, and y squared is called C. The basis vectors are called like this. And we define a new space Y. And Y should be the ring homogeneous degree 2 polynomials. So it should be the homogeneous degree 2 polynomials in the variables A, B, and C. Okay, so this is the basis here. It's a 6-dimensional vector space. You can think of those as, homogeneous degree 2 polynomials, but the variables here are actually also the monomials in your original polynomial. 6-dimensional vector space, and there's a natural way of defining, again, with this, what is called the canonical pullback, again, defining an action on this space here, on the 6-dimensional vector space, by already having an action on the 3-dimensional vector space. So tau f is defined by its evaluation at p, by just say, okay, I evaluate f at tau p. Right? It's exactly the same as we did here. We do it now here. And let me just maybe quickly show you. So tau maps A to C, B to B, and C to A. As we've seen here, right? This is just this one here, right? This is just what I wrote here. But then in a natural way, it maps a C. If it maps A to C, then it maps A squared to C squared, right? And AB is mapped to CB and so on. So in this way, we get a completely natural action of tau here on that 6-dimensional vector space. Right, and yeah, so this decomposes. So a 6-dimensional vector space has a 4-dimensional space of invariance and a 2-dimensional skew invariant space, like here, like 4 and 2. And this is already a Plethysm. So if you understand now these numbers here, then basically you understand what a Plethysm coefficient is. It's these kind of numbers, but it's for a more difficult group. So we don't take the group S2. We take the general linear group, and then that's the Plethysm coefficient. Okay, that's all there is, right? Then you have a definition of a Plethysm coefficient. So the general linear group, unfortunately, is a bit more complicated, and I will quickly go through this. It's not so completely crucial. Okay, so you first of all, V is a GLV representation by just, I mean, if somebody gives you some element in GLV, you just apply it. That's just your usual matrix vector product. You can think of that. You can make the polynomials, say homogeneous polynomials of degree m on V. You can make it a GLV representation. Is again exactly as we did before. So this is the one canonical way of doing it. The transpose here is just for technical reasons. This doesn't matter. The transpose was not there before because the tau was a self-transpose, right? So therefore it wasn't there. And again, so exactly as before, we have a representation, we lift it to polynomials of degree n, right? So it's exactly in the same fashion. It's a bit difficult here if you've never worked with this. This is in this short time frame, it's very difficult to see what's happening. It's actually a little calculation to see that the discriminant here, b squared minus 4ac in our example that we had before, in this case here, m is 2 and n is 2 and v is also two-dimensional. If you act with any element here, any matrix, then this will rescale only the discriminant by the determinant of g squared. This is a little calculation that you need to do, but I will need this for the examples later. Okay, so now what I want to do is, so we in the previous examples, we were now looking at the invariant space and the skew invariant space. But now but this is only because the group S2 is so simple. There were only these two different spaces. But now the general linear group is much more complicated. And therefore, there are more irreducible representations of the general linear group. And let me quickly tell you what that is. And then you will have the complete definition of the Plethysm coefficient that we want to look at. First of all, the subrepresentation is just some linear subspace that's closed under the group action. And we've seen plenty of those already. I mean, here in this example, you can, for example, take b squared minus 4ac. Since it only rescales, this is a subrepresentation, right? So the line spanned by b squared minus 4ac, it lies in this space this notation is of course terrible, and there are other notations for this. But for this, I didn't want to introduce much more notation for the talk. So this is the notation, it's the C2, it's polynomials homogeneous of degree 2 on the space, and it's homogeneous polynomials of degree 2 on that space. So this is our 6-dimensional vector space from before. And this is a 1-dimensional linear subspace, and that's a subrepresentation here in this case. And an irreducible representation is just a representation that has only 0 or w as subrepresentations. Now, every finite dimensional just ignore this. Every finite dimensional representation now is a direct sum of irreducible representations. And this is what we want to look at. And we want to count how many irreducible representations are in our decomposition. So the vector space decomposition that we had for S2 was really nice, but for GLV is a bit more difficult. It actually involves weight vectors and highest weight vectors. So I need to define that, and then we will be there, okay? So let's just assume our vector space V is C to the M, okay? And now what's a weight vector? A vector of a certain weight lambda in any GLV representation W is a vector where if you act on that vector with a diagonal matrix, right? This is a matrix that has alpha 1 up to alpha m on its main diagonal, and the rest is all zeros. Then that vector just gets rescaled. I mean, getting rescaled, like the discriminant, just gets rescaled when you act on it with some group element. And here's some exponents here. These are natural numbers. There's just some exponent here. Yeah, so it rescales. Those are your field constants here, and these are complex numbers here, alpha 1 up to alpha m, and lambda 1 up to lambda m are integers or natural numbers. And a vector is of highest weight if additionally you have that if you act with an upper triangular matrices that has ones on the main diagonal, then it's fixed under that. So this is a bit a tough definition here. Let me give you this example. For example, if you take again the b squared minus 4ac is the discriminant, and you know that if you act on the discriminant with a matrix with a sum any like 2 by 2 matrix here, invertible 2 by 2 matrix, then this rescales with a determinant of g squared. So this is the same vector but just rescaled, and therefore b squared minus 4ac is the highest weight vector of weight 2, 2. So why is that? So why is it a weight vector of weight 2, 2? So let's just check. I mean, if you have a matrix 2 by 2 diagonal matrix, there's an alpha 1 and an alpha 2 on the main diagonal, and you apply that to the discriminant, what happens is that the discriminant rescales with the square of the determinant, but the determinant of a matrix that has an alpha 1, alpha 2 on the main diagonal, and the rest is zeros, that's just alpha 1 squared times alpha 2 squared. Right? So therefore, it actually indeed rescales with an alpha 1 squared times alpha 2 squared, and like the rest is just zeros here. So this is a 2, 2, and that's the weight of the vector. So the discriminant has a weight 2, 2, and it's a highest weight vector because, say you have an upper triangular 2 by 2 matrix with ones on the main diagonal, then the determinant of that is 1. Right? If the determinant is 1, then this means that determinant squared is also 1, so the discriminant is actually fixed. Okay, so the discriminant is a typical example of a highest weight vector. So why are these highest weight vectors interesting? Because they describe basically the irreducible representations. So yeah, a lot of things, basically they describe the whole representation theory of the general linear group. You have that every irreducible GLV representation contains a unique highest weight vector up to scale, and two irreducible representations are isomorphic if and only if the weights of their highest weight vectors coincide. This means that the highest vector, basically, the highest weight vector up to isomorphism completely defines the irreducible representation. Yeah, it's this will always be a partition, so there's always lambda 1 greater or equal to lambda 2 greater or equal to lambda 3 and so on. So this will be a non-increasing sequence. And indeed, to each partition, there exists an irreducible representation. So the partitions completely index the irreducible representations. And now we can say, what are these multiplicities that we want to look at? So the multiplicities that we want to look at are the dimensions of the space of highest weight vectors of a certain weight lambda in W. So let me maybe remind you. So the first examples with S2, we were looking at invariant spaces and skew invariant spaces and their dimensions. And we called this like these were multiplicities, these dimensions. Here the multiplicities are a bit more difficult. Though the multiplicities are still dimensions, but they are dimensions of highest weight vectors of specific weights. Okay, and so different you are varying lambda and you get different highest weight vector spaces and you take their dimensions. And we call those multiplicities because if you decompose W into a sum of irreducibles, the multiplicity will tell you how often the irreducible appears in the decomposition. That's where the name comes from. So that is a very natural number to compute. And yeah, we can define now a Plethysm coefficient here, which is a lambda nm, which should be exactly a multiplicity like this, but for a very specific representation. In this case here, it's exactly the representation that we were looking at. It's the homogeneous polynomials of degree m on some vector space V, and you take homogeneous polynomials of degree n on that space. So this is, of course, a bit a difficult notion. It will not be so crucial it will not be so crucial in the upcoming discussion, but I just wanted, this is about Plethysm coefficients, so it needed to have some proper definition, and it is the definition that we use actually in the paper. So there are plenty of definitions also using Schur functions and things like this, but this is the one that actually can, this is the one with the highest weight vectors, is the one that actually makes everything work. Yeah, some context about this coefficient. So this is called the Plethysm coefficient. Dates back to very early invariant theory, actually. Whenever you study algebraic varieties of polynomials that are invariant under where the varieties are invariant under base change, you will always encounter these coefficients. So, for example, you study Waring rank. This is a special type of tensor rank. Then you will encounter these coefficients. And so, for example, there's some very old results here about these coefficients. 1845 is Hermet's theorem on reciprocity that a Plethysm coefficient, if you switch n and m, then it stays constant. It stays the same, provided that only lambda 1 and lambda 2 are non-zero. And yeah, this is just so highlighting some interesting properties and a conjecture. So this is a big conjecture here, is Folk's conjecture from 1950, that the Platism coefficient nm is always greater or equal to the Platism coefficient mn whenever n is greater or equal to m. Right, so I got interested in these coefficients because they appear in geometric complexity theory, actually in several occasions here. It's not, yeah, it's several occasions. So when you find them all over the place, and they're intriguing. There's no combinatorial description known. So this is problem 9 in Stanley's list of problems, and you could formally phrase that as the function mapping lambda and m to the Platism coefficient is that in sharp P. So can you, I mean, it's defined as a dimension of a vector space, but we don't know of any nice basis of that vector space. If we would have some nice basis in terms of combinatorics, that would solve it. There might be some other way of solving this and finding something that does not involve finding a basis, but certainly, yeah, but this is the big open question about these coefficients. And yeah, so there are some complexity results about them, but not many. So this is the one that I found, is that you can compute it if n is fixed, if so n is fixed. But we will actually fix m and see then if m is fixed, then this is actually hard. So this gives us actually a nice contrast, right? Fixing n, it's body time. Fixing m, it's actually NP hard. Okay, I give so how do we prove now that the coefficient is hard? So I give some combinatorial interpretations for this weird number in special cases. Okay, so this was the definition of the coefficient, but it turns out that working in this space is a bit messy. It turns out that there's a nice duality theorem that tells you that you can actually work you take the vector space V, you raise it to the nth wedge power, like skew symmetric power, and then you raise that space again to the nth skew symmetric power. So this is a bit of a complicated space. Let me give you a nice basis of that space so that we know what we're talking about. Fixing m equal to 3, okay? I give you a basis of this space now here so that we are on the same page. So Vi should just be a basis of V, okay? Finite dimensional vector space, no problem. And our basis of the third wedge power of V is given by these vectors here, Vx, wedge, Vy, wedge, Vz, where you have x is less than y is less than z. So those are your basis elements, okay? You can denote them like this. And indeed, we should think of these basis elements as actually being defined by their triple xyz. So the open cone, we call it the open cone, is just xyz, where x is actually less than y is less than z. And now a basis of the nth wedge power of that is given by n tuples. So you can think of them as like n points in three-dimensional space that lie in this cone here, x less than y less than z. So we call these point sets. So you think of this three-dimensional cone, and in there you have like n points. And they give you a basis of this space. And so the interesting thing now is that these basis vectors, they are already weight vectors. So we don't have to find somehow which are weight vectors, is some linear combination. What is a weight vector here? No, I mean, each basis vector here is a weight vector. And the weight of that vector is what we call in the paper the sum marginal. So you just take your set of points and you just ask how many of my coordinates of all the points that I have are 0, and how many of how often in all coordinates does 1 appear, or does 2 appear? So this is what this is. So for any point set P, you define as IP as the number of times the coordinate I occurs in any point. But this is just formally as IP. You take all the points x, y, z in your point set, and you're just adding. This is a Kronecker delta, right? You're adding 1 if your coordinate is equal to I. And the sum marginal is just, yeah, is S0, S1, S2, and so on. For example, say you only have 2 points in your point set. So what's S of P? This is the number of zeros here in this list. Basically, you just take this list of numbers, counting the number of zeros, counting the number of ones. There's a 1. There are 2 2s here. There are the 2 2s. There's a 3, there's a 4, there's nothing else. This is called the sum marginal. This is the weight of this vector. It's very easy to extract that from any point set by just taking this list and writing that down. But the amazing thing now is those are weight vectors, and what we want to count is the dimension of the highest weight vector space. So every weight vector, not every weight vector is a highest weight vector, but every highest weight vector is a weight vector. So if we know the dimension of the weight vector space, which is precisely the number of point sets where the sum marginal is exactly this lambda transpose here. Yeah, the transpose is a technical thing, just comes from this duality here. Don't worry about this too much. So with the correct sum marginal, this gives an upper bound for the Platism coefficient. So this was dimension of the highest weight vector space. This is the dimension of the weight vector space. And this has a combinatorial description, counting these point sets. Okay, so an upper bound, there's a combinatorial upper bound now. That's already very good. So we only need to have a combinatorial lower bound now for this coefficient. And we can also get that in the same type of language. And it's this one here. So this is
maybe before you go to the next slide, let's ask if people have questions.
Oh, yes, please go ahead. Yes. This is here's an upper bound on the coefficient. This is the dimension. This is combinatorial. You're counting points now. It's a bit weird that you're basically counting. It's a bit unusual that you would just count all the zeros in like the whole list, right? This is not what you usually have when you're talking about marginals, but here this is exactly what you have. But people might have questions about that. I completely agree.
Okay.
That's okay. All right. Yeah, there's not much time anyway. So, okay, there's an upper bound. So to prove hardness, we need some combinatorial interpretation of this coefficient. We have a combinatorial upper bound. We get a combinatorial lower bound now, so that we have some combinatorial interpretation. Because without a combinatorial interpretation, it's very difficult to prove hardness of the coefficient. But getting a combinatorial interpretation, then it will be possible. So a lower bound is now needed. And we also get that. Let me maybe, let me define how to get the lower bound. So you have in your cone, where x is less than y is less than z, you can define a layer. Like your points come in different layers, say, which is just the sum of x plus y plus z. Okay, you think of your three-dimensional cone, and you have a layer 3, for example. 0 plus 1 plus 3 is 3. 0 plus 1 plus 2 is 3. 0 plus 1 plus 3 is 4, right? You're just summing up. And they come in different layers. So you slice your cone. And I want to define a pyramid as a point set that contains all the points of all the layers up to some layer. And then it might contain some points on layer k plus 1, but it does not contain anything in layer k plus 2 or higher. This is also a combinatorial thing. And you can count the number of these types of pyramids for sure. And the interesting thing is now, that you can prove is not very difficult. If you have a pyramid as your point set, then the corresponding weight vector is a highest weight vector. So all these pyramids give you highest weight vectors, and they are all linearly independent because all the basis vectors were linearly independent. So therefore, you get exactly this a minus now, a number of pyramids, and that would be a lower bound. So here we have an upper and a lower bound now for the Platism coefficient. This is just any point set with a specific sum marginal. These are the pyramids with a specific sum marginal, and they squeeze the Platism coefficient. And this means that whenever you have a minus is equal to a plus, then there's a combinatorial description. And that's perfect because the combinatorial description now enables you to do whatever you want. I mean, you can prove hardness now with this description. So you can go from 3D to 2D. I mean, I have I think very few slides to illustrate now what's happening, but this is basically a key thing. Now there's a combinatorial interpretation. And so what you end up with is having this combinatorial description of the Platism coefficient in this very specific cases now enables you to prove some really interesting things. Say somebody gives you this is a proposition. Somebody gives you an instance of a problem or what is called the skew-symmetric 2D X-ray problem. Then you can compute actually a lambda tilde such that the number of solutions to this problem equals the Plethysm coefficient. Now, this is now possible and not too difficult to do because you have actually the subcase where it is actually a set of combinatorial objects, right? So you can prove such a proposition, and these problems are just are very a natural problem. So you have a triangular grid, and you want to have specific marginals. Here is, for example, let me explain this. There's 2 points, 2 fat points here. And this is the triangular grid. There's X, there's Y, there's Z. You have a point 3, 2, 1, you have a point 5, 1, 0, and they are sitting here. And you have an X marginal, which is, there's a 3, there's a 5 in X. There's a 3 and a 5 here. 0, 1, 2, 3, 4, 5, right? This is this 3 and this 5. There's a Y marginal having the 2 and the 1, right? Having ones here. And there's a Z marginal. And this is the sum marginal, as before. I just take them all. And there are two problems related to this. There's, first of all, the 2D X-ray problem. We know already that is a hard problem. So somebody gives you the 3 marginals here, X, Y, Z. Does there exist a point set that has these marginals? And that's already known to be NP complete. And the skew-symmetric version is now a bit a weird version that people have not looked at before, but that is the one that we need for the Platism coefficient. So somebody gives you only the sum marginal. Does there exist a point set in the cone that has the sum marginal? But it is similar, right? So, and then, so the main point are two, this slide basically contains all the things that you need. You have if somebody gives you a 2D X-ray instance, mu, nu, rho, and we know that that is hard, right? So you will not be able to solve that in polynomial time because it's an NP-hard problem. We have an algorithm that gives you a skew-symmetric 2D X-ray instance that has the same number of solutions. But if you have a skew-symmetric 2D X-ray instance, you can actually find some lambda tilde such that this is the Platism coefficient. So you can this means that every 2D X-ray instance you can find some Platism coefficient who's not, where the Platism coefficient is in the number of solutions exactly to your 2D X-ray problem. But then it cannot be easy to decide positivity for the Platism coefficient because that would be enable you to decide this 2D X-ray problem, right? So this is called a parsimonious reduction, and and there's a cool picture here. I don't think this is. I don't want to go into the details here, but the main idea is you need to somebody gives you an X marginal mu, a Y marginal nu, and a Z marginal rho. You have to somehow create some new sum marginal, and this is how you do it. You pad it with exactly correct, you put rho and a bunch of zeros, and nu and a bunch of zeros, and mu and a bunch of zeros, exactly in the correct number of zeros. Then that will be your sum marginal. And you will find actually a bijection of solutions to your original problem, which is written in like a tiny triangle here, to some much larger problem here, where you actually find this here. So yeah, if you have a solution to the 2D X-ray instance here, then you can find the solution here to your large skew-symmetric 2D X-ray instance. So this is actually bijective. You find anything here is here, and vice versa. So the proof works so that you all the solutions to your skew-symmetric 2D X-ray instance here, which is the big triangle, all the points lie actually in this white space here. Because these zeros here, they will clean out. The zeros say basically that you cannot have any points in these colored regions. So all the colored regions are cleaned off by the zeros, and you can only be in the cone, and this would be the only thing that's left. So it's a bit technical, and this is actually the technical heart of the proof, but it is, the technical heart of the proof uses only elementary combinatorics. There's nothing else to that. All right, that's that. So I hope that I could, the main point is the Platism coefficient, if you want to show hardness, then you need to have a combinatorial interpretation in some subcase. And once you have that, you can use your usual things that you do, like parsimonious reductions and so on, to actually prove the NP hardness of the decision problem. Yeah, that is what I wanted to say.